Suppose I have two electrons and they're entangled. How would I know if they're entangled? If I have two electrons, let's say, and they're in a singlet state. If I now separate these two electrons, and now once they interact with their environment, the spin might rotate. So now when you try to bring them back together, you might not be able to. The sensitivity in typical SETs, single-electron transistors, is roughly 10 to the minus 4 of 1 electron. And you can ask, well, why is this useful? I don't have 10 to the minus 4 of electrons, I only have electrons in nature. The reason is that if you're trying to detect an electron that sits here and you're far away, let's say, only a small fraction of the field lines from that electron end up on your sensor. So you're going to be picking up something that's much smaller than 1 electron. Most of the things, the kind of fun things that happen in the lab, you discover, you didn't expect. You plan an experiment, the experiment fails, but then it fails in a really interesting way that teaches something new about what is going on.
This week, Misha spoke with Dr. Amir Yacoby, professor at Harvard University, whose work is pushing the limits of quantum measurement. Yacoby explains how physicists build ultra-sensitive quantum sensors to detect single electrons, map nanoscale systems, and uncover new physics in both quantum materials and qubits. Please welcome Amir Yacoby.
I very much like the process, and the process sometimes involves being challenged by some interesting prediction and kind of scratching our heads to figure out how would we probe or check whether these ideas are consistent with what's happening in an experiment. Sometimes we stumble upon a phenomena that we kind of didn't understand, and once we figure it out, we realize that we can use it as a new type of sensor. So I like the process primarily, much more than any individual type of technique or sensor.
Sounds like a detective story.
Absolutely.
Finding out how this thing works.
Yeah.
So could you give maybe an example of what's like maybe on your mind right now, or maybe in the past, which made you scratch your head really hard?
Yes. So let me give you one example. Early on, actually, when I was a junior faculty, we were looking at one-dimensional systems. And the way we made these one-dimensional systems is very, very similar to the way you make two-dimensional systems, like MOS, like MOSFETs, basically. And in gallium arsenide, you do that by having what's called modulation doping. So you have a quantum well, and if above that quantum well you sprinkle some dopants, the electron from these dopants would fall down into the quantum well. To make a one-dimensional system, you can imagine taking this quantum well, cleaving it, and now growing on the cleaved edge and sprinkling charge. Now when the electrons fall into the quantum well, they're already confined in the quantum well direction, giving us a very, very high-quality 1D wire. And this is something that I worked on during my postdoc. Was really fun and exciting, really high-mobility wires. You can imagine electrons in these wires. Like if you think of the Holland Tunnel in New York, then, you can shoot an electron all the way. The aspect ratio is really that, and it has no scattering as it goes all the way through the Holland Tunnel. Kind of really long mean-free paths, fractions of millimeters. And what we decided to do for some random reason was to grow two of these wires in parallel. And just to look at the tunneling between them, and our motivation was there was some predictions about suppression of the tunneling when you tunnel into a one-dimensional systems, and we wanted to see that. I remember I was in the lab and I told my student, hey, let's kind of ramp the magnetic field. We'll look at the tunneling and see what happens in the function of magnetic field. You kind of press the button to ramp the field. I look at the lock-in amplifier and, tell me if something happens, I'll tell you stop. And then we'll kind of focus on it. So we started doing the experiment, and then very soon after...
What was the magnetic field?
So the magnetic field was applied perpendicular to the wires. And, we didn't really, because the electrons are so tightly confined, you wouldn't really expect the magnetic field to do much at all, because the electrons can't bend because of the Lorentz force, because they're already confined in this very narrow channel. So we didn't really expect much, but I told my student, hey, if something happens, just let me know and we'll stop the ramp and we'll explore.
What was the magnitude of the magnetic field?
Oh, magnitude was, we had a field that could go up to several Tesla, but once within a few hundred Gauss, immediately kind of lock-in amplifier starts showing crazy response. And I told my student, okay, stop. Let's figure out what's going on. And then we slowly started kind of...
Sorry, maybe like one more question. So did you apply like voltage, like to send the current in one wire and then observed in another one? Or it's
so
like
we sent the voltage between the wires.
Between the wires.
So imagine you have two copper wires and they're very close together and you're just applying a voltage between them and you're letting electrons tunnel.
Line, kind of.
Yeah, like a transmission line. And is something going to happen when you apply a magnetic field? And so, immediately we saw a huge response and I said, okay, let's stop. Something is going on. We need to figure out what's going on. And it took us a couple of months. But what it turned out is that the electrons in the wire, they have a well-defined momentum. And because of the precision of the growth, what happens is when you tunnel an electron from one wire to the other, momentum needs to be conserved. So if the two wires have different dispersions, right, k squared in one and maybe a slightly different density the other, the Fermi momenta, the momentum at the Fermi energy do not match. But what happens is when you apply magnetic field, and we didn't realize that immediately, what happens is that one dispersion shifts in momentum relative to the other. So the magnetic field gives you a slight momentum boost. And suddenly these two Fermi surfaces would overlap and would give you, right, as you move these two parabolas, one versus the other, at some point they will cross. And at that crossing, suddenly you get a huge current.
I see.
And so we figured out that, we developed something new that we didn't kind of plan.
How did you find the crossing point?
It's because there are two crossing points, right? So if I have two parabolas and they're slightly different, you see that there's going to be one that appears very soon and the other one that appears at much larger magnetic fields. And we saw these two crossing points.
But when you did the experiment, did you already know what you were doing?
No, we didn't know what we're seeing and why we're seeing it. It took us a long time to figure this out. Actually, Bert Halprin from Harvard here helped us in understanding what was going on, etc. And then we realized that once you apply a bias, now you can shift these two parabolas vertically, one with respect to the other. So now you can see how one Fermi point can map out the dispersion of the entire other wire. And so suddenly we had a very, very nice way of experimentally mapping out the full momentum resolved dispersion of electrons in 1D. And physics in 1D is really interesting because electrons are really not the elementary particles in a one-dimensional systems. Charge waves are basically, these are plasmons, are the elementary excitations. They can have fractional charge, and their spin and their charge get separated. So imagine you have marbles that have a color, and you have, red and green. Imagine that you could move the marbles without moving the color, or just moving the color without the marbles. So this is what happens in 1D. For some reason, the spin and the charge degree of freedom decouple completely. And
how's it explained, like in terms of, it's just mind-bending, I guess. Especially it was like at that time.
Yes, because these all have to do with interactions.
With the environment, right?
With between the electrons, and the fact that the dispersion is one-dimensional. Basically, the fact that you're only able to move in 1D is responsible. This is a physics that really only emerges in 1D. And the interesting thing is that the speed of the spin waves and the speed of the sound waves is different. And this kind of dispersion mapping allowed us to see in detail the dispersion of the spin waves and the dispersion of the sound waves. And it was kind of really exciting. And it all was serendipitous. We didn't plan on doing any of that. And in fact, a lot of these ideas of momentum resolved tunneling are now being used by my first student Shachalilani, who's doing these twisted experiments in graphene. They built this kind of twisting microscope. And there now in 2D, you have momentum conserving tunneling between the electrons in one surface and the other, and the same kind of ideas of mapping out a dispersion using this kind of momentum conservation is employed there. So this is one example where, and this is really the kind of things I really like, is when you discover something and then you realize you can use it as a really effective tool to study interesting physics in a condensed matter setting.
This was here at Harvard? Or
No, this was when I
Weizmann?
was at Weizmann. Yeah, just as a junior faculty. We had a different, so, there are many other examples of kind of serendipitous discoveries. I mean, most of the things, the kind of fun things that happen in the lab, you discover, you didn't expect. You plan an experiment, the experiment fails because you see something different from what you planned, but then it fails in a really interesting way that teaches something new about what is going on. And if we can give more examples if you like.
And then, so how did you start working in the lab, like maybe with this 3-5 materials?
Yeah. So when I was a graduate student, I did a lot of experiments with Moti Heiblum. So he was just starting his appointment at Weizmann. I was his first student there. And we did a lot of experiments on 2D electron systems, high mobility.
So as a first student, usually you're the one
who sets up,
who needs to set up the lab. And
oh yes, I spent months and months and months putting evaporators together and setting up Dill fridges, etc. It's a great experience. I tell my students that if they have a chance to go and work with someone who is a junior faculty for grad school, then that's a big, big plus. It might take them an extra year, but they will learn so much from doing it. I'd recommend it less in the postdoc phase because that's kind of a more
short term.
You need to really get things
fast,
exactly.
quickly.
Yeah, but yeah, no, I had experience, and I could certainly say that my first students who helped set up my lab at Weizmann, and then my lab here, etc., were all very successful because of the experience they got. It really sets you up for success.
So then coming back to the times in Weizmann Institute. So you said you were like the first student of the group, setting up the equipment.
Yes. So that's when I was kind of starting as a grad student. Before that, I did theory. Actually, I was working with Joseph Imry. He's no longer with us, but he was kind of the father of mesoscopic physics. And I did a master's thesis with him. Always my kind of hope was to do some theory so that I can understand theory better, but I mostly kind of wanted to do experiments. So this was planned.
It's like a big jump.
Yes, basically from theory to experiment. But it was I really wanted to do that. I wanted to have the experience of doing some theory so that I could understand theory papers better, talk to theorists kind of in a more effective way, and it helped. Yeah. So I tell my students if they can take a class in field theory or kind of really up their game, the theory understanding of what they're doing, it's going to help them tremendously as experimentalists.
It's interesting. I think I've seen this trend that theoretical physicists, when they establish their group, it at some point becomes an experimental group.
In some areas it works. In condensed matter, I think it's quite rare to transition from theory to experiment at a late stage, once you're kind of developed. But during your kind of studying phase, that's okay. Because, theory and experiment, they're really, you need to be a professional, and you don't want to be the best experimentalists among the theorists or the best theorists among experimentalists. You really want to be the best in the area that you're working on. Yeah.
Maybe we can come back to even like earlier times. Maybe like in general, a question like what brought you to the area of maybe like physics, theoretical physics at some point?
I didn't study, I flunked physics in high school. if I were to apply based on my high school diploma to colleges in the U.S., there's no way I would be admitted to any kind of decent. I was not interested in studying at that point so much.
What were you interested in?
I was interested in airplanes, actually.
Oh, wow.
And so eventually I studied aerospace engineering. This is my undergrad degree is in aerospace engineering. And after that, I worked a little bit in the industry as an engineer. But realizing that I wanted to study more, go beyond the bachelor's degree or engineering degree, I came to realize that in engineering, you're not going to have much use for a PhD, let's say, in the aerospace industry. I mean, you might be a group leader or something like that, but you really, it's not that needed. And I said, I want to study anyway. So I switched to physics at that point and decided to do a little bit of theoretical physics. And that kind of, transition to physics was not that easy. I had to, supplement quite a lot of material.
It feels like it's, I grew up like in Russia, and then there was a big difference in cultures between like engineering and physicists. Like here in the US, it seems like it's, I would say, like mixed depending on the schools and the university. But
but topics like, quantum mechanics, statistical mechanics, were not even covered, obviously, in aerospace engineering. There's no need to know any of that. Or even high level of, electricity and magnetism, all these things. I did know thermodynamics pretty well and how engines worked,
right,
and how a jet engine worked, but it wasn't useful for a physics degree, kind of. So I needed to. And then I remember, to be admitted to Weizmann in physics, there is an interview, and I came with very little background in physics. So the committee, who sat, 3 professors, were sitting there and interviewing me, and they were very kind. They said, "Hey, why don't you tell us about something that you're familiar with and interested in, and we'll kind of explore that." So we talked about things like lift, etc. But then they posed this question of, suppose you have a spaceship and it's orbiting Earth, and it's like it's a sphere, and you're inside the sphere. Where would the dust accumulate? Was the question. So of course I didn't get the right answer, and they helped me. But eventually, the answer is kind of fun. And I often ask students when I want to interview and see how people think on their feet. I ask them this question. And the dust accumulates on the point closest to Earth and the point furthest from Earth. And the reason, of course, it's the same reason as the tide. Why you have 2 high tides and 2 low tides per day. But what happens is that in the center of the sphere, gravity and the centrifugal force cancel.
Yep.
But if you go a little bit closer to Earth, now gravity is larger than the centrifugal force, so you're pulled towards Earth. And if you go a little bit further away, then gravity is a little bit weaker than your centrifugal force, and so you're pulled away. So it basically kind of pulls everything to the 2 extremes. And that's what happens when the moon, kind of acts on Earth. If you think of Earth as covered with water, then what would happen is that you'll have more water towards the moon and more water further away from the moon and very little water on the sides. And so now you see you have 2 high tides and 2 low tides as you spin around. So it was kind of a simple, it was a very tough question, and I, of course, didn't succeed with it. But they were at least kind to kind of respect and ask me something about space. Yeah.
What about like the culture of the Weizmann Institute? How do you?
Yeah, it was actually fantastic. The lectures. So because Weizmann does not have an undergraduate degree, so everybody comes from different institutions to study a master's or PhD there. And so they have these first 2 weeks, which are like a catch-up, basically, to bring everybody to the same level before the semester begins.
So Weizmann is more like a research institute, essentially?
It is a degree offering institutions, but only from masters and PhD. So there is no undergrad. So it's some kind and something in the middle. But yeah, no undergrad research. So there are no undergrads there.
I don't think we have like similar institutions in the United States like that.
I don't think so. I mean, and it's not like the Max Planck, because Max Planck does not
research
provide degrees. You need to kind of couple with a university next to the Max Planck so that you can get your degree there. But the Weizmann is an institution granting degrees, but just masters and PhD. And so you have postdocs, etc., faculty there, but not undergrads. But during these 2 catch-up weeks, lectures were, you really kind of very quickly were brought up to speed so that everybody's more or less on the same level of the undergraduate knowledge.
And it's both for theorists and experimentalists.
Yes, for everybody the same, yeah. And then courses, I mean, I have to say, still look at some of my notes, especially if I want to teach a course kind of in the, a graduate course. They were really amazing. Very lucky to have such good teachers there. Yeah.
Afterwards, you transitioned like from Weizmann to, was it, how was the transition happen?
So from PhD, master's at Weizmann, and then PhD at Weizmann. In fact, I started doing my PhD with Moti Heiblum when he was still at IBM. So the first year of my PhD I spent at IBM Yorktown Heights, and did some experiments there. And then when Moti moved to the Weizmann at a point where, so I basically started my building before my PhD, before there was even a building to do the research, right? They were building a new building, kind of a mesoscopic center. It was called the Submicron Center. And so yeah, it took some time to get things into the building and all the clean rooms
Special
working.
Facility requirements.
Oh yeah, absolutely.
Which years was that?
That was 1994 or something like that. 1989. So 1990 to 1994 was my PhD, something like that.
So people didn't yet talk about like nanotechnology.
No, not nano. And mesoscopics was just kind of the word, the buzzword then. Basically, people started to understand much more about the electronic properties and, decoherence, right? The notion of, today we talk about decoherence a lot for qubits, etc. The notion of coherence was not well understood then and kind of only started to be discussed then. What does it mean that an electron is moving coherently inside a solid, etc.? That's
interesting. I would assume people know about coherence from light experiments like electromagnetic waves.
Yes, but like inside a solid,
project to
but interference gets lost when particles interact with many other degrees of freedom. So now you have an electron inside a solid. There are 10 to the 23 other electrons.
Yeah.
Would you expect to see any coherence in an experiment where electrons are kind of moving across the solid? And that was not understood. And it turned out that, yes, you would expect to see coherence and, elastic scattering, for example, by impurities will not destroy the coherence. So things that were very intuitive for us today were very, very controversial and being kind of figured out then. Kind of very interesting period.
I see. So it's like when you can, I guess, do you need to localize essentially to observe the coherence properties?
So you don't need to. So what, some experiments that we did, for example, very similar to optics experiments, but you would launch, so inside a solid, you would create kind of a point contact. You would launch electrons from a point.
Injecting?
Like injecting, yes. So you'd use metal gates to block electrons so that they can only move through the channel, through a narrow opening. And then you would detect them on the other side, and now you could change their wavelength, etc., and see whether you get interference. So the first experiment I did was exactly an interference experiment, seeing very clearly interference of ballistic electrons in 2D. There was a lot of discussion about how electron-electron interactions causes loss of coherence, and what is the temperature dependence of that, and how does the dimensionality of the system matter if you're in 3D or 2D or 1D. All that was very, very interesting and emerging at the time.
And I understand it was fueled by the discovery of the quantum Hall effect, like fractional.
So that was a little bit separate. So quantum Hall effect and fractional quantum Hall effect was known at that point. So, kind of the big, it started, right, quantum Hall effect was early 1980s. Fractional quantum Hall emerged 1983, I think. And, very fast after that, people started to understand a little bit better what's going on. Mesoscopic physics, I'd say, started kind of the interesting time was 1986, 87, 88, and onwards. So yes, what the effects of magnetic fields would do, etc., but not necessarily very strong magnetic fields. So it was very separate. But then slowly the combination, right? So doing an interference experiment in the presence of a quantum Hall system. So now you have the edge states and how they interfere. And actually, a lot of the ways that people are using interference today started from those old days and are able to give you information on fractional charge and fractional statistics. So these are kind of topics that are still very much interesting today. Non-abelian statistics, these are good platforms to explore.
So then jumping to the Harvard times.
Yes.
How did the story continue here? What happened to you, like transitioning set from Weizmann to Harvard?
So I spent a sabbatical here 2003, 2004, and from the Weizmann, and had a great time, and the family enjoyed it a lot. So we decided, when the opportunity came to move here, we decided, hey, it's something that we'd like to do. So we moved, and that happened more or less 20 years ago. So this summer it's going to be 20 years at Harvard. Quite.
It's like anniversary celebration.
Exactly.
Congratulations.
So yeah, I set up a lab and obviously had some additional resources to try new things. So one of the first things that we did here, so during my sabbatical, I actually had a lot of fun working with Charlie Marcus on spin qubits. And, some of the first spin qubit experiments were actually done here when I was working with Charlie. And, we were trying to think very hard.
So were you already thinking in terms of quantum computers? Like,
yeah, absolutely.
You call them qubits already?
Yeah. So this was 2004, something like that.
Okay.
And I remember having conversations and saying, so, suppose I have two electrons and they're entangled. How would I know if they're entangled? What would I do? And, we were kind of brainstorming. And, eventually we came up with the idea that if I have two electrons, let's say, and they're in a singlet state, if I separate them,
does it need to be that the superposition, single state up, down, plus, down, up? Or?
Up, down, minus, down, up, let's say.
Up, yeah.
But if I now separate these two electrons and let them kind of spend some time, and now once they interact with their environment, the spin might rotate. So now when you try to bring them back together, you might not be able to, because the singlet state is a low energy state, and if you rotate and you suddenly transition to a triplet, that has a much higher energy state. And so basically that's how we kind of came about the idea of qubits that are encoded in singlets and triplets. And, one of the students then, Jason Petta, he was a postdoc, I believe, at the time, did these experiments of separating and bring them back together and seeing, whether you come back or not. And
how do you physically do that?
So you electrostatically. So what you do is you have two quantum dots.
I see.
And you put one electron in each, and you can now push, right? Kind of basically electrostatically, just try
We're
to
talking
push.
about quantum dots as like defects in the...
No, these
like
are quantum dots in a semiconductor. So
Semiconductor.
imagine you have a 2D electron gas, and so we started doing all that in
Yeah,
gallium
like this, let's
arsenide.
say the gallium arsenide multilayer and
Exactly.
the defects.
Yeah.
I see.
And now you have metal gates, and these gates can deplete and remove charge from everywhere, leaving just charge in the regions that you want.
Mm-hmm.
And you can really see very effectively if you have 0 or 1 or 2 or 3 electrons in each one of these dots. And then you can try to push basically just electrostatically. You repel an electron from here, and it then wants to move to the other dot. So this way you can control whether the electron's really kind of trying to push one on the other or not.
How do you measure? Like, how do you distinguish how many electrons?
Yeah, so there are many different ways. One is you could use a single electron transistor. So basically, you put a very sensitive charge sensor nearby. And then what happens is that it can sense very effectively the electrostatic configuration of electrons. So if I have one electron here and one electron here, and I have a charge sensor here, it would see some potential due to that charge configuration.
So charge sensor is like a tip you bring, like the
charge
SCM
sensor
tip?
is something that's called a single electron transistor. This is also an interesting story.
Maybe if you could
yes,
explain
I can
it.
explain that. So single electron transistors are, again, a topic that was a study of exploration in the early 1990s. It started with two types of experiments. One at MIT by somebody by the name of Udi Meirav, working with Mark Kastner, who then got the Buckley Prize for one of these, for basically single electron transistors. And there, what they found is, again, in gallium arsenide, they created a very narrow channel and long. So they tried to make a one-dimensional system. We talked about one-dimensional systems.
Right.
They did it in a very different way by electrostatically depleting a 2D system to form a channel. And they were looking at the conductance of this channel, and suddenly they saw that the conductance would open up and close and open up and close, and producing this kind of very periodic arrangement. And initially they thought they had a Wigner crystal, so the electrons were organized, but eventually what they realized is what they have is kind of a quantum dot, and the charge in that dot is discrete. I'll explain more. The other group that saw similar physics was Dolan and Fulton at Bell Labs. And what they did is they took aluminum and then another metal island that was only tunnel coupled to these two electrodes. And again, what they saw is that the current from one electrode to the other through this metal island had these kind of discrete peaks in conductance. And, again, after some time, they figured out that what's happening is that the charge on the island is quantized. It has to be an integer. You can't have half electrons. And as you're trying to charge this island, charge can only enter or exit this island discretely. And because of that, the conductance through the system would show peaks only during the time where electrons are allowed to go on or off the island. So basically, you get this very sharp charge peaks, which then they turned into a sensor. So suddenly you have the conductance, which is extremely sensitive to the environment, because any little change in potential will change the current on this peak, right? So I could maybe sketch something on the board.
To me, it's also like fascinating from a tool perspective that you can measure to charge of a single electron.
Right. So maybe to explain this a little bit, imagine you have a capacitor. So you have some plate and another plate, and you apply a voltage between these two plates. So you want to charge this capacitor. The energy on this capacitor, we know, is given by Q squared over 2C. So if I am to plot the energy versus charge, it's a parabola. But the interesting thing is that because this has a finite size, the charge on this axis is not continuous. I'm not allowed to choose any value. I can choose discrete values of charge. So I need to look at discrete points on this curve corresponding to n electrons, n plus 1, n plus 2, etc.
And
now,
then why n gives you the minimum there? Right?
Yes. So the minimum here is actually given by, so the minimum of the parabola, E min, is given under the condition where Q equals C times V. V is going to be, is this E.
Yes.
So again, you see that it doesn't have to be the minimum because this needs to be N times E.
Mm-hmm.
C is whatever it is. V is continuous. I can change it continuously, but this needs to be discrete. So you can imagine two different situations. One that looks like that, where the minimum is indeed N times E. But you can have another situation where the minimum is, let's say, N plus a half.
Mm-hmm. Just by adjusting the voltage.
Yeah, you just change the voltage a little. Mm-hmm. So now what happens, this is going to be N, and let's say this is going to be N minus 1. The minimum here is, sorry, this is N, so this is going to be N, this is N plus 1, and this is N plus a half, which is not allowed. But you see now that N and N plus 1 have the same energy. So this means that at this point, the system can fluctuate and charge can go on and off the island, but here it can't. Because here it's N going to N plus 1 or N minus 1 costs energy. So if I look at the conductance, so if I do an experiment which looks like that, and there's this voltage V that I apply.
Mm-hmm.
This is some tiny bias that I try to send a current through. What you'll see is that as a function of this gate voltage, Vg, there will be conditions in which current can flow. This corresponds to this situation.
Mm-hmm.
And then, so this would be N plus a half. This would be N plus 1, not allowed. Current cannot flow.
Yep.
And that's why you get these peaks in conductance, which count electrons. So you could see each electron being added to this device one by one. And this slope here is determined by temperature. So now if you want to convert this to a sensor, what you do is you sit here. And now you monitor the current of your device, and any tiny changes in potential causes changes in current, and you can detect it. So this is how you turn this into a very, very sensitive sensor.
What temperature do you need to have to start resolving those peaks?
So typically it's going to depend on the size of this island.
Okay.
But, in our experiments, it's, below 2-3 Kelvin, you could easily resolve.
And size of the island?
It's maybe 100 nanometers. Yep. Which is nice because both you get a spatial resolution now because, anything that happens within this dimension is going to influence you. And if you're far away, you're not going to detect it. So you're going to detect only things that are very local. And you can get very high sensitivity. Just to give you a sense, to go from here to here is 1 electron, right? This is 1 electron.
Yep.
So the sensitivity in typical SETs, single-electron transistors, is roughly 10 to the minus 4 of 1 electron. So you can detect tiny, tiny changes in charge. And you can ask, well, why is this useful? I don't have 10 to the minus 4 of electrons. I only have electrons in nature. But the reason is that if you're trying to detect an electron that sits here and you're far away, let's say 100 nanometers away, only a small fraction of the field lines from that electron end up on your sensor. So you're going to be picking up something that's much smaller than 1 electron. And you do need this kind of 10 to the minus 4 sensitivity. And we've been using this technique. So this is something that I joined as a postdoc at Bell Labs. I joined at some point.
Oh, you also at Bell Labs?
I was at Bell Labs, for 3 years,
How was that? Yeah, so this
Yeah,
is
yeah. Well, it was an amazing experience. So I started working at Bell Labs on these wires that we discussed with Horst Stormer, who was the person who discovered the fractional quantum Hall effect and won the Nobel Prize
wow,
for the
that's
fractional
amazing.
quantum Hall effect. Yeah.
So you worked like in his group, or
Yeah,
how was
yeah,
it?
yeah. I was working directly with him. And then during my last year there, I became a full member of what's called member of technical staff, and stayed beyond the postdoc for some time, and worked with a person whose name is Harold Hess, who then later developed some amazing techniques on super resolution microscopy. He's a very inventive person. Very well known for doing some very classic STM experiments into vortices of superconductors. And then, and with Ted Fulton, who's the person who invented this discovered this single electron transistor phenomena. And when I joined them at the time, they were already developing a tip, basically a scan probe, that has one single electron transistor sitting on its end, in order to be able to measure potential very precisely as a function of position. So they invented a new probe, which is called the scanning single electron transistor, which we now use in our group a lot. They used it before I joined. They used it to look at defects, basically, to see where kind of ionized in a semiconductor. When I joined, I started kind of applying this technique and inventing its use for interesting problems in quantum Hall physics, to measure, for example, where are the edge states, to see the Landau levels, the compressibility and incompressibility of the system, to measure fractional charges and fractional quantum Hall effect. So all these things came later, but using this technique that I learned at Bell Labs.
So is it still up to date, the most accurate sensor, precise sensor for measuring the like charge?
For measuring charge, it is definitely one of the more precise ways. In fact, if you were to do this measurement at high frequency, if the physics allows that, then you can even get it down to 10 to the minus 6 of 1 electron. Later on, when I was doing work on spin qubits, we figured out a way to get even better sensitivity. So going down to 10 to the minus 8 of 1 electron charge. And that was really using coherent control of a spin qubit. So you could ask, well, what's the connection between spin and charge? So you remember when I described this kind of separating electrons and connecting them, it turns out that the physics is very strongly sensitive to a gradient in magnetic field. So if I had a magnetic field gradient and I had the two spins, what happens when I separate the electrons, suddenly the two spins feel different magnetic fields and they precess in a particular way. And then when you try to merge them back together, it either works or not, depending on how long they were separated. But the point is that now if I know what the gradient is, then I could extract information about how easy it is for me to separate them. So if I'm trying to detect a charge that is, its influence is to separate the two electrons, I could do it with a precision of 10 to the minus 8 of 1 electron. And I think we even had a patent on this, if I'm not mistaken. Or they said, oh, it's going to only work at low temperatures, so maybe it's not going to be useful for anything. I don't remember what the discussion with the university was. But yeah, so you can invent very sensitive ways of detecting things by, harnessing various phenomena. Like this phenomena is called Coulomb blockade. The fact that you have to have discrete number of charge. And with the spin qubits, it's basically what's called singlet triplet qubits. You could get a very sensitive charge sensor just by doing coherent manipulation. Quite similar to the ideas of, how NV centers measure magnetic field, then this specific spin qubit is very sensitive to electric fields.
I see. Although NV center is, I feel like, sensitive to almost anything.
It could be
Temperature,
that's right.
stress, electric field, magnetic field.
Yeah. With the varying sensitivities, obviously, it's mostly sensitive to magnetic fields, less sensitive to electric fields or temperature, etc. But of course, if you have something that is within its sensing range, then it's a very, very nice probe.
So on industrial level, let's say for like foundries or for the companies who grow the semiconductor materials and want to make sure that estimate what's the impurity level, because it's do you know, like, are these do they use these techniques or this is too expensive in terms of like too slow or not?
Well,
not so scalable?
it's problematic in multiple ways. Number one, it requires low temperatures.
Yeah.
So that, I think, is not. I mean, semiconductor companies, what they would like. Number one, they'd like something that gives you information fast on very large areas.
Right.
Two, they'd like to be able to just take their process and kind of in the middle of the process. But if you need to cool something down and approach, so it's kind of not very, very useful. At some point, I had some collaboration with Brooker on scanning NV magnetometries to make basically to build sensors that rely on magnetic field sensing and what you could do with that.
And Brooker, they do like AFMs, and then
Brooker, they do AFMs, but they also do all your NMR.
Right?
Yeah, but all NMR and MRI instruments are Brooker. And what we showed is that using an NV center, we can do 3D magnetic resonance imaging, but now with a spatial resolution of a nanometer rather than a millimeter, which is what you have in hospital equipment. So again, but you need to bring a tip very close, etc. So not always very practical.
Can you do it in 3D space, or it needs to be?
Yeah, it's a fully 3D reconstruction of spin density. And it's actually, usually with MRI, you need to make a lot of assumption about what's called the point spread function, where, if you had a source here, what would your image look like? Let's say you need to make some assumptions about that. With NVs, you actually measure that intrinsically. So there are many less unknowns, and you really can construct fully the three-dimensional configuration of fluctuating spins. Electron spins are far easier than nuclear spins, but in principle also nuclear spins if their density is large enough.
Yeah, I think it would be great if you could also explain. Probably you need some explanation on the bit of like NV, how it works.
Yes, so
for
we
the magnetometry, and then for the MRI.
Yeah, we could definitely talk a bit about that. So first of all, NVs. NVs is a relatively old topic. People study defects in diamond for quite some time, but then the breakthrough was a group in Germany, Jörg Wachtrup, basically, whom was able to isolate a single NV and start studying its properties. And once what they realized that it has a fairly simple spectrum that we understand. And, maybe kind of a small digression. The way you develop new instruments is by harnessing some piece of physics that you understand, which allows you to connect things that you know how to measure with things that you're interested in reporting. Easy example is GPS. You want to report position. We're measuring the time it takes the signals to arrive from the satellites, and the physics that connects the time to position is general relativity. So once you have general relativity, it's kind of something that we can rely on, and you can connect these two quantities. So with NVs, it was the same. Basically, the thing that we're measuring is fluorescence. We're scattering photons off of this defect and collecting photons, but we understand its level structure very, very well. And we understand then that the amount of photons that we can extract depends on whether the spin of this defect is up or down. And so we understand its properties very well. I could provide some more, if you like, on the board.
Yeah, I think it would be. I mean, up to you. It's illustrations on the board. I like the board style.
Board is good. Board is So NBs have a defect. So that's the magnetic field. This is the energy. It's a 3-level system that has 3 levels. Ms equals to 0, ms equals to -1, and ms equals to +1. And the slope here is basically just given by, so the energy here is just given by G times mu times B. So the slope here is just given by the G factor of a free electron, G factor of 2.
Weizmann effect.
Just the Weizmann effect, that's right. You have something that's called zero field splitting, something like 2.87 gigahertz, has to do with the diamond lattice. So now, interestingly enough, when you shine green light, let's say on this defect, what happens if the electron sits in a ground state, it gets excited to some high energy optically active state and then comes back and emits a red photon. But if it occupies one of these states, ms equals ±1, it turns out that it has another pathway of relaxing that emits less photons. So the intensity depends on whether you're ms equals 0 or ±1. So now let's consider we initialize this defect, and you initialize it again just by shining light into the ground state. And you want to know what is the magnetic field that you're at. You don't know it. So what you do is you come with some microwaves at a frequency omega. And you scan this frequency. And now you're looking at the intensity of the fluorescence. So when you're at low frequencies below this energy, so you're looking for a condition where the Weizmann energy equals h bar omega. So if omega is below that, nothing happens because you can't absorb.
Mm-hmm.
And if it's above it, nothing happens because you can't absorb. But on resonance, suddenly you get an absorption. And if you get an absorption, your population now gets split between the ground state and excited state. Your fluorescence drops. So you see a dip in fluorescence at the frequency omega, such that is given by G nu B, from which then you know what B is. So this is typically the simplest way of using an NB center as a magnetic field sensor, again, because we understand this level diagram very well. There are more sophisticated techniques that use coherence and creating superpositions of multiple levels, etc., that can give you far better sensitivity. But this is kind of the simplest one that one could use. Okay, so now if we want to talk about magnetic resonance imaging, so you know, in magnetic resonance, what typically happens is that suppose I have a magnetic field. So if this is position and this is magnetic field, in a magnetic resonance, I have some field gradient, such that if I have, let's say, a body here, person, what I would then look for, I would look for precession, and if I detect a precession at a particular, so the nuclear spins will precess at different frequencies depending on what the local magnetic field is. So when I look at the spectrum of magnetic field and I find something corresponding to this frequency, I know it comes from this position. And if I find something at other position, I know. So this is how I get spatial information from the magnetic resonance. With NVs, it's basically the same idea. If I have my NV center sitting here and I have some sample.
Do you mostly see likewise like absorption of?
Yes, so usually, you know, magnetic resonance imaging, you have some pickup coils, they're far away, and you're basically looking for the radio frequency emission associated with the nuclear spins and how they're basically generating the signal that your pickup coil picks up. But to get the spatial information, you encode it. And again, this is kind of very basic. There are much more sophisticated ways of doing it today, where you encode the information in the phase. It's more complex, but the basic idea is that you have, for example, here, different frequencies give you information on different locations. With the NV center, it's basically the same, that the idea is the same. If I create a magnetic field gradient across this structure, then again, I would be able to pick up the precessing magnetic field based on that contour. But the nice thing is, because the NV is a spin itself, it can measure, right? It basically provides a direct measure of what the magnetic field environment is. And once you know that, that's what's your point spread function. You can use that to reconstruct from your measurement now when you're looking at the sample. But, and yes, you can, it's a very sensitive sensor, so now you can get nanometer spatial resolution rather than kind of fraction of a millimeter, which is what commercial instruments give you for magnetic resonance imaging.
And what are like the requirements for the magnetic field gradient?
Right, so that's interesting. You're absolutely right. So obviously, suppose in your experiment you're able to discern, so can you discern two frequencies that are separated by a hertz, by a millihertz, by a nanohertz, right? There's going to be some noise. We're going to have some detection limits. And so the bigger the gradient, right, you're going to be able to detect the smaller spatial scale for the same change in frequency. So you really want very large magnetic field gradients. Typically in MRIs, you're going to have something on the order of 10 Tesla per meter. This is already very big kind of field gradients.
Wow.
In our experiment, what we did is we had some magnetic particle, and in the near field of this magnetic particle, the magnetic field gradients could be on the order of 10 to the 6 Tesla per meter. So that's why you gain so much in spatial resolution, because the field gradients in the near field, very close to some very tiny magnetic particle, are crazy. Really, really big. So
you need to have like this magnetic defects or something like that, or
yeah. So you have So what we did, for example, is we had an NV. So we had some diamond. We had an NV center inside the diamond, and we had a bunch of spins, let's say on the surface, some spin density that we wanted to image. And so we'd come now with a tip, which is now a magnetic particle, and we'd scan that around relative to the position of the NV. So first of all, the NV allows us to map out what the magnetic field this particle is producing. And then once you tune to the resonance of these spins, you can now map out their density and get that in 3D. So you can really see how well localized they are in Z and how far they span in XY, etc.
But this is, the spins needs to be positioned practically on the surface of the diamond.
No, they could be, I mean, that was easy for us, but they could be in 3D.
Okay.
Because the field gradients that you're producing, you have gradients both in the depth and laterally, right, from this particle. So you can get full 3D construction of spin density using this technique.
So what kind of interesting samples did you measure this one?
We did not pursue this further to measure interesting samples.
Oh,
I
really?
think it would be very interesting to use this. So, the technique works for what's called paramagnetic spins. So spins that are not strongly interacting, which is what you have. Nuclear spins in your body, they're too far apart for them to really interact strongly. And the idea is then that when you have a field gradient across, only a small subset of these spins will be in resonance, and you can flip those and not flip the rest. So now you're getting a signal from a small subset. For most of the systems that I'm kind of really interested in condensed matter, the interaction between spins is very strong. In a ferromagnet, for example, right? Suppose I have a ferromagnet. So all the spins they're strongly interacting to give you an ordered state. If I put a gradient field, I'm not going to be able to flip this spin with respect to the others because there's such a strong interaction between them.
So flip the neighbors probably.
Well, it might flip everything, etc., but it's not going to give me this kind of local spatial resolution. So it really doesn't work when I have strong spin-spin interaction. So it's really good for paramagnetic spins, nuclear spins, or free electrons, which was here, in this case, was just the surface of diamond. But in condensed matter, you need to develop different techniques, and that's why we developed these kind of spin wave scattering experiments that I could talk more about, actually really fun. But these are the ideas is to study interesting phases in condensed matter. So maybe we spend a minute on that?
Yeah.
Yeah?
Definitely.
Okay. So let's talk a minute about spin waves.
I see spins is like manipulating, measuring spins comes through your whole career, right?
Yeah, absolutely. Spin and charge. So interacting phases of condensed matter physics, they are all kind of driven by the interactions of spin and charge inside the solvent, many-body physics. So imagine I have a ferromagnet. So the ferromagnet has very strong spin-spin interaction, and under certain conditions, all the spins want to align. Now, if I'm able to perturb the spin and tilt it a little bit, it's going to push on this one, and it's going to push on this one, and I'm going to get a spin wave. And this spin wave has a dispersion. So if I were to draw the energy versus momentum of the spin waves, then, in the simple just exchange only, I would get something that looks like a parabola. Under more interesting conditions, you can have dipolar contribution, long-range interaction, which would flatten this dispersion, but it's not so important. But I have some dispersion. So now, how would I launch spin waves? So number one, how would I excite them? So imagine I have a piece of ferromagnet. In our particular case, it's called YIG. So what we do is we'd put here an antenna, and we basically send a current, I, at some frequency. So what this current through this wire here is doing, it's generating a magnetic field, which is time dependent at frequency omega. And that magnetic field wants to tilt these spins, and therefore would launch a spin wave in this direction. And you can ask, well, what is the momentum of this spin wave? Well, the momentum is just given, so if this is omega, it's given by the frequency and the dispersion. So I'm going to get. So now the question is, okay, how do I know that I did it? How would I detect it? So envies here, people, just to give credit, people have developed many different techniques to detecting spin waves, like Brillouin light scattering, etc. But I'm going to talk about NV detection of spin waves. So how would I detect it? So I have here spins that are wiggling in time, and each spin is a dipole. So it generates magnetic field. So if I were to position my NV spin somewhere in the vicinity, it's going to pick up time-varying magnetic fields. And as we already talked about, if this is the spectrum, if that frequency is resonant with the NV, I would see a change in fluorescence, so I'd know that something is happening at that frequency. So this is how I would detect the spins of the NV. The spin waves. I want to point out that what's propagating here is a spin wave that has a frequency and a momentum. And this is the momentum that's given. And these are traveling waves. And in fact, when I sit at a particular point here and try to measure it, I'm going to see I'm picking up this frequency component. So if I were to talk a little bit, go a little bit deeper into the NV physics, so I have a block sphere describing the state of two levels, where let's say this is the 0 state and this is the 1 state. So I have here the 1 state and I have the 0 state. What happens when I have a time-varying magnetic field, I get Rabi oscillation. So if I start with my spin here, this frequency, time-varying magnetic field, is it's basically like a vector here that wants to rotate my spin. So this is this magnetic field here, B. And so my spin is going to rotate around this axis from 0 to 1 and back to 0, etc. And I can detect it. What is the role of this phase? So the role of this phase is to choose. So you see, I drew this green arrow along the x-axis, but I could have drawn it also along the y-axis. And it doesn't matter where it's pointing in the plane, because it's going to take me from 0 to 1.
I guess B field would define it. Or?
So what the phase defines is exactly this angle. So you see that around what axis we're processing in the plane here is dictated by the momentum and by position. But if I'm only measuring whether I'm at 0 or 1, it doesn't matter around which axis I'm rotating. I'm just going to see that I'm rotating. So in order to determine this phase component here, what we do is we send another time-varying magnetic field, B of t equals e to the I omega t, with no position dependence. So just from some wire, from some electrode. And so the field that the NV sees is the sum, this plus B naught e to the I omega t, without a momentum.
And
so
X
this is the spin wave.
Propagation direction, that's the perpendicular one.
X is propagation.
Okay.
So the spin wave is producing me a time-varying magnetic field due to the spin waves, let's call it Bs. And it has a phase that's changing with position. But I also have another uniform magnetic field that I generate by another means, another electrode, that has no position dependence. So now you see that the intensity of the e to the I omega t is given by 1 plus e to the I kx. In effect, on this picture, if this is if this is B naught pointing, let's say, in this direction, at different phases, you see that these two things add up like vectors. And I would have a direction for which this phase exactly is a minus sign, exactly cancels out this contribution.
So tune the parameters until you see.
Yeah. So just as you move your NV now, what's gonna happen? You're gonna get an image that shows the wavefronts, because only at specific positions do these things cancel, and you get strong fluorescence. Other positions you get weak fluorescence.
And dark.
Dark, bright, dark, bright. And these are exactly separated by k times x equals pi, 2 pi.
So then
you can
know
really
the periodicity of the
you can really image these propagating spin waves very, very nicely. So then once we saw this, we said, well, okay, what could we use this for? This could be fun. So we thought about what other experiments people are doing with waves. And every scattering experiment is an experiment with waves, right? So imagine like X-ray scattering. What happens? You have a source. It's producing some X-rays. That's impinging on some target and diffracting. And by measuring somewhere far away the amplitude and the phase of the scattered X-ray, you can then reconstruct what scattered it, right? This is how scattering experiments. You do it in optics, you send in optics, you get some diffraction, a hologram, all done by scattering. So he said, oh, interesting. We now have spin waves. Can we do a scattering experiment? So can we take our material and launch spin waves, but somewhere downstream put a target of interest?
But you don't really need the NV center because you already know from your source what kind of wave you send, which direction.
Well, you need the NV center to see how the
scattering pattern, I see.
Exactly, that's the whole point.
Okay.
So what you get out here is some scattering pattern, and we image that with the NV in order to reconstruct what the target is. And so this is really cool. You know, so for spins and spin waves, the canonical technique is what's called neutron scattering. But these are kind of big facilities. You take a neutron, you scatter it through a magnetic material, it diffracts, you collect the neutrons, but you need a big volume in order to scatter the neutrons. Here what happens, we can do it with one monolayer, 1 micrometer in size, and we're going to get very effective scattering already. So it's designed for a different regime that neutron scattering cannot address, which is much smaller sample size, mesoscopic sizes, maybe interfaces. Something interesting is happening between the interface of this material and the substrate that we're launching the spin waves on, etc.
So what neutron scattering is used these days for?
It's used for, to measure ferromagnets, antiferromagnets, to get the magnetic structure. There's something that's called altermagnets today, some new type of magnetism and new. So, you know, you have ferromagnets and antiferromagnets, and now you have altermagnets. So these are alternative. It's actually alternating. I don't remember actually which one they thought of. But yeah, so neutron scattering is used to characterize materials. Usually it's bulk materials. You can't do it for 2D or 1D. But this technique might work. And this is still a lot of work in progress that we're developing, but it's kind of a cool idea of developing an entirely new scattering platform using spin waves.
And what kind of information about the scattering object do you care about or would like to know?
Right. So you'd like to know whether, for example, are there domain walls here? Are there, any interesting, the way the magnetization arranges itself within this? Because in a finite, if this was a big sample, then you would say, okay, boundaries don't matter, etc. But now you have something that's fairly small. It's interacting with the substrate, which could influence its properties quite a bit. So you want to know, what is the magnetization doing? Now, you could say, well, why don't I directly just image the magnetic fields coming out in this region? But this is a static process, right? You're picking out the static magnetic field. This is a scattering process, so you're looking at how the system responds to a finite frequency and finite wave vector.
And then you can sweep the frequencies.
Sweep the frequency, sweep the wave vector.
But you're limited by NV centers. What's this? The bandwidth.
Yes, that's exactly correct. So one of the limitations of NV centers is that typically it's a narrow bandwidth sensor. Basically, you're measuring at the frequency that gives you a resonance between the ms equals 0 and ms equals +1. The second thing that you're limited to is by the distance of the NV to the sample. So you want to kind of work on both. So we're doing a lot of work right now to increase the bandwidth of the NV center so that you're not only limited to working at this specific frequency.
What is it now in terms of numbers?
It's a couple of
from
gigahertz.
DC to gigahertz.
It's gigahertz, yeah, which is very good for these systems actually, because a lot of the spin wave spectrum is in the gigahertz range. Ideally, if you have antiferromagnets, then you have a lot of things happening at terahertz. This is really challenging for NV centers, but we have some ideas.
Are the defects?
Yeah, maybe. Well, the problem is just delivery of signals, right? And the terahertz, just generating it's
Like a source to generate the spin
the
rate.
source and detection and how to extract and all the terahertz optics becomes really hard. But very interesting and good type of challenge to develop it into the higher and higher kind of hundreds of gigahertz maybe first and then terahertz.
Yeah, that's really fascinating. And are there any alternatives to NV centers, like to measure locally? I guess.
Yes, absolutely. So, today as technology improves, people are making superconducting qubits that are tunable, right? And the way you tune them is with flux, for example. So you can make a transmon qubit. A transmon consists of some capacitance and some nonlinear inductance. And that gives you a superconducting qubit. But now this inductance, you can make it to be sensitive to flux. So now you could think of, well, hey, can I use a transmon to do some spatial imaging of magnetic fields? Now, the problem is that transmons are huge.
Big, yeah. Can we make them smaller?
Well, so you don't need
Just
to
for
make the
sensing purposes.
transmon smaller. And people have done, this is work that started, again, many decades ago with SQUIDs, just a SQUID, basically a superconducting quantum interference device. You can make a SQUID that's fairly big, but now what you want to do is you want to have something that's called a flux transformer, right? So imagine I have a SQUID, which looks like that. It has two Josephson junctions. And this is, let's say, big, maybe hundreds of microns or a millimeter.
What's the, why does it need to be that big? What limits its sizes?
It's just easier to make. It's just, but, and there are nanosquids. So when I was at Weizmann, the way we made the single-electron transistors was by taking a quartz rod, 1 millimeter rod, and you pull it. You can reduce the diameter by kind of heating it up and pulling.
Pulling, yeah.
Right? So you would end up with something that
sounds like with the fibers,
Yes, exactly. It's like a quartz fiber.
Quartz fiber, yeah.
Actually, when I was at Bell Labs, we started with 100 micron fiber and we pulled it down to 100 nanometers. And then I transitioned to 1 millimeter quartz rods that we would pull down. But the idea was that you then evaporate from one side to give you metal here. You evaporate from the other side to give you metal here. And then finally you'd oxidize. And you'd evaporate from below to give you metal here, and that gives you your single electron transistor electrode, small particle electrode. And this you could scan around. But when I was at Weizmann, we developed, so we pulled hollow rods. So that now what happens is you get a metal ring. When you deposit from below, this is hollow now. So you get a metal ring, and you get one Josephson junction in the coupling of this superconductor here, and another Josephson junction here. So you really get a squid like this on a tip.
It's like, what is it? How many angels can dance on the tip?
Yes, like crazy. So we have a patent on this, and then my collaborator at Weizmann, Eli Zeldov, he took it and really did beautiful science with this. Turns out that, these things can measure temperature with extreme precision, kind of down to the, below a microkelvin sensitivity.
So this is, yeah.
So scanning
it's a squid on the tip, right?
Yes, squid on the tip, and this is maybe 50 nanometers in diameter.
Wow.
But what's very easy to do is on a substrate is a big squid. But now what you can do is you say, suppose I want to pick up flux from some really tiny region. So what you do is you define something that's called flux transformer. Right. So now so if you put a flux here, if this is all superconducting, The superconductor doesn't want to have flux go through it.
Right.
So what would happen when you put phi here, you're going to get minus phi here. So you just transmit, basically. So now you can imagine building a scanning apparatus where you have a big squid and then a pickup loop that brings the flux to your sensor.
Squid, I see.
And this could be a squid, it could be a transmon, because the way you would measure a transmon is kind of more taking advantage of coherent control, like a qubit really, could have better sensitivity, etc. So we are now developing a platform. We talk about how many angels. So we're developing a platform now where we can put multiple sensors on one tip. So we're developing a pyramid in silicon, where on this pyramid we can put an SET, we can put a squid, some RF resonator. On the side here we can have transmons or whatever you want. On the side this is big, and you can have a pickup loop then that takes you to the transmon. So all this thing is now kind of on chip. Parallel processing, so we're making many of these tips at once, and we can simultaneously now image magnetic fields, charges, conductivity, many different things at once. And this is kind of something that we've been working for the past couple of years on, and we're starting to do the first measurements are happening now.
Maybe like for the broader audience, if you could go through like a bit, touch on the basics of the Josephson junction, like SQUID-based sensing.
Yes, absolutely.
And why is it now like mostly one of the most common magnetic sensors? SQUIDs?
Yes, absolutely. Even there are squid arrays that are being used to try and measure, brain activities. Again, the challenge is that you need low temperature. If you could replace that with NV sensors, that would be room temperature, but now you need optics, etc. So there are advantages and disadvantages. Here you just need some electrical circuits. But yeah, so basically the idea, so let's see how we can describe a squid easily. I mean, I could just describe maybe the phenomenology.
Sure. Yeah.
Right, so if I have a squid, squid is a superconducting quantum interference device. And you can see that if you send a current I here, what happens is that the current gets split between the two sides.
Mm-hmm.
And now it turns out that if you thread a flux here, then the total current that basically can flow through this device before it becomes normal. So this is all superconducting. So current flows here without resistance.
Mm-hmm.
But if you increase the current too much, it'll become normal.
Critical current.
So that's the critical current, right? So if I plot here current versus flux, what you find is that it looks like that. Where this is phi naught to phi naught, and phi naught is just h over 2e. So it's a tiny unit of flux given by fundamental constants. 2e is because this is superconductor. And you see now that, and this is the critical current, so the system has zero resistance within these lobes. And then once you exceed that critical current, you see that you get a resistance. So the idea here is if you had a way of measuring what the critical current is in this device, then it will tell you, if you sit, for example, here, you have a bias flux, that tiny changes in flux will give you changes in critical current that you can then measure. So by measuring the current, you can infer what the changes in flux are. So that's how the SQUID measures flux very sensitively. And the idea here was exactly the same. You have this hole, And once, so you see also the advantage of a big loop is that it can detect very weak magnetic fields. So the sensitivity of a squid, delta phi, is given by sensitivity in flux. The sensitivity of an NV center is delta B. Right? The relationship between flux, this is some delta B times an area. So if I have a very big area, I can detect a very small magnetic field.
That's why squids are probably big.
That's why squids are big,
That was a
but you
sensitive
lose
one.
spatial resolution.
I see.
But if you can now focus the flux that you're interested in onto the squid, now what happens is you have some delta B here. This delta B times the tiny a gives you a flux, and you see that the flux that you get here is still tiny because this a is small. So the fact that, so, you know, it's the size of the pickup loop that's going to give you the how well you can detect magnetic fields. But for certain phenomena, you're interested in detecting flux and not magnetic fields, for example, vortices, etc. But yeah, but basically this is the trade-off. The trade-off is magnetic field versus flux goes through the area.
And those two arms you need for like interference?
Yes,
I assume,
exactly.
So that gives you the lobes?
Yes, that gives you the lobes. Yeah, I could go if you want a little bit more in detail, or
Sure, we
it's good enough.
could touch a little bit more if you have some.
Whatever is kind of interesting. But so the way this works,
It's like a pretty complex things behind, like to understand fully. But I think it's good
right?
to have
So,
like a
so let's consider a
simple
single
explanation.
Josephson junction. Turns out that in a single Josephson junction, there is something that's called current phase relation. So a superconductor has a amplitude and a phase, and so if I have a Josephson junction here, so basically two superconductors coupled through some weak link, the current is given by some I0 times sine of the phase difference phi across the junction. So this is the Josephson, kind of fundamental Josephson relation. And you see that the current can never exceed I naught. That's the critical current.
Mm-hmm.
If I send a current that's greater than I naught, I cannot satisfy this equation and the system goes normal. Okay? Now let's consider what happens if I have...
So is it like a sine probably square or something like
Yes,
that?
so what happens here...
Oh,
is
because we have two, I see.
you have
Multiple.
two of them, right? So the current, the total current here, let's call this I1 and I2. So the total current I is given by I1 sine, there's going to be some delta theta 1 here and delta theta 2 here. Different phase. But note that this phase has to be the same, and this difference is the same, but what the flux is doing, it's gonna, the total integral, so you have to have what's called continuity, or, you know, the phase has to add up to a multiple of 2 pi as you go around.
Mm-hmm.
So delta phi 1 plus delta phi 2, we call it theta. 2 plus phi has to equal multiples of 2 pi, let's say 0. So now you see that if I put here delta theta 1 plus I2 sine delta theta 2, I can replace delta theta 2, let's say, by phi, right? So delta theta 2 is given by minus phi minus, so you could put here minus delta theta 1. So now I can write this as I1 sine delta theta 1 plus, so there's a minus sign here, so it's minus I, this is some I0. This is just the critical current of the junction. Sine of phi minus delta theta 1. And delta theta is just, kind of a phase that I don't need to worry about so much. But you see that now I get an interference as I change the flux. I get an interference between these two currents that can add constructively or destructively. And that's what gives you these modulations.
Yeah. Digging deeper into SQUIDs.
Yes.
Yeah.
Yeah.
Okay. And then you do this SQUIDs on the smaller scale, and then you can integrate it into the chip. And then
Yes, exactly. And you can have the big squids and just have a pickup coil. So all these things are possible.
So what's in general, like if we take the most sensitive, I mean, I understand there is a trade-off between resolution and sensitivity of the magnetic field. So what is the state of the art, let's say, on both sides?
So I would say, when I compare techniques, it's always good to, in comparing techniques, it's always good to remember that there are many different parameters that technique operates in. So for example, NV centers, there's nothing that could allow you easily to measure magnetic fields with the precision that NVs have at, let's say, 50 Kelvin. Right? Because SQUIDs require low temperature. They're superconducting devices.
Yep.
So in principle, you could say, well, I could use a high temperature superconductor. They're not so easy to work with. And so suppose you wanted to measure magnetic fields at a 300 Kelvin or 1,000 Kelvin. So SQUIDs are just not going to be useful there. Certainly SQUIDs could be very effective at very low temperatures. One of the things that are not so convenient with SQUIDs as well is that they need to operate low magnetic fields. You can't put a very large magnetic field on a SQUID because the flux is going to affect its performance. NVs, you can't put very large magnetic fields also, but you can put some reasonable fields, a couple of kilogauss, it'll still work. You need to maybe care about the direction, etc. I think SQUIDs could probably, there is something that's called RF SQUID, so you can make the SQUID work at higher frequencies. In principle, it might be easier to make a broadband sensor with SQUIDs than it is with NV centers that have a resonance that you need to kind of match. So I would say there are pluses and minuses. With NVs, you can always, if you don't care so much about spatial resolution, you can have many of them. You can have an ensemble. With SQUID, you just increase the area, and now you are sensitive. So if, the magnetic field that a SQUID could be sensitive to for large area SQUID, it would be hard to beat with a NV sensor. But on very small scale, probably NVs are kind of pretty darn good.
I see.
Yeah.
Yeah, we have heard from Ron Bosworth.
Oh, yeah.
They were using this NV-based sensor platform for, what did they study? Almost...
they study biological systems. Yeah,
and then the geological
samples. Yes, and a lot of our work initially when Ron was here was in collaboration with Ron. I still have a student now that is formerly Ron's student, but is doing his work here. Just graduated recently. So yeah, I love working with Ron.
I see. So what is, let's say, so you're basically like constructing sensors which can be high precision, spatial precision, as well as high sensitivity in terms of like the fields. Or so what would ideally you would try to measure? Yeah.
So part of our reason, part of our reason for developing this kind of sensors that have these probes that have multiple sensors on them stems from layered materials. So, in a layered material, you take, let's say twisted graphene, just as an example. As a function of density, the system goes from being a superconductor to being an insulator with some interesting properties. none of these sensors individually are good for measuring both an insulator and a superconductor, right? SQUID is very good for measuring superconductors because superconductors, they repel flux. So you're going to see some response when the system is superconducting in the SQUID. But a single electron transistor measures charge. And when the system undergoes a transition to a superconductor, there's going to be very little signature on that channel. But now if the system becomes an insulator, goes from a metal to an insulator, the SQUID would not care so much because if there's no magnetic field information in there between the insulator or the metal, it's not going to detect anything. But the single electron transistor is going to detect a big signature now because suddenly the way charge gets screened in a metal or an insulator is very different. So because you can go from these different phases just by tuning a gate in these systems, we wanted to have sensors that could target all the different phases. It turns out that in some of these systems, like twisted graphene, etc., we don't, we can characterize largely what the phases are. They're superconducting, they're insulating, but we lack quite a bit of information. What is the underlying order parameter, for example? So you have a superconductor, but is it an S-wave superconductor? Is it a P-wave super? Is it topological? Is it chiral? So there are a lot of questions we don't really know, and we wanted just to be able to bring more and more probes so that we could basically ask many questions, the same device, simultaneously, to be able to kind of figure out really kind of in detail what is going on. So that was our motivation for why, we know how to make a scanning SQUID, we know how to make a scanning SET. Now we wanted to put them all on the same probe so that we can simultaneously see, in space, where are the superconducting phases? Where are the insulating phases? Can we correlate? Are the superconducting phases magnetic or not magnetic? Every piece of information we can.
And you can do measurements instantaneously for like both.
So that's our goal. So right now we're developing the various probes. The fabrication technique is such that it allows us to put multiple sensors of different type at the same time, and we have all the electronics in the fridge that we need in order to measure these sensors simultaneously. So it's still kind of building up, but yes, that's where we're headed. Yeah.
And what's the main challenge of this kind of co-integration of the SEM? It
was
sensors?
Actually a huge challenge to develop these probes, and right now we've figured out the fabrication. But the main challenge has to do with the fact that you're trying to do high resolution fabrication on surfaces that are not planar.
On the tips, essentially.
Basically on the tip, yeah. So we start with a silicon wafer, and then we etch it down to form pyramids, which are our tips. And we need to separate these probes one from the other so that eventually we can break it and mount it. And then we need to do all our patterning to pattern the SQUIDs and the Josephson junctions and the SETs, which require multi-steps, all on non-planar surfaces. And fabrication, you spin resist. It doesn't like it when your surface is not flat.
Yeah.
So we had to kind of really scratch our heads quite a lot, and the students who have worked on this really kind of did an amazing job, and now we have working process finally. It reminds me a little bit when we were developing our scanning envy centers experiments. We started out by saying, well, let's pick up nanodiamonds, just some particles. Let's kind of attach it to a tip and hopefully, and then, we sometimes succeeded, sometimes very non-reliable, until one of my postdocs, Patrick Malatinsky, who's now in Basel, professor, he said, okay, we need to do this kind of really robustly. And he set out to fabricate tips out of bulk diamond. So starting with kind of a chip of diamond, thin it down to maybe 30 microns, and then etch pillars, and then etch the platform that the pillars stems from, etc. And that fabrication development took a long time. Now we have it kind of routine, and we know how to get them out when we need to. It takes maybe a round of fabrication, maybe takes 2 weeks or so. But to develop these processes takes a long time to figure out all the pitfalls and where things go wrong. Yeah.
Yeah, can imagine. That's like mind-bending from the fabrication perspective, and then so many steps,
It's
and
really tour de force to get these kind of
one of its
sophisticated
kind
products.
sensors.
Yes, yeah, very, very nice. But with NVs now, there are multiple companies who, including Patrick, he has a company that sells
Those tips or
tips and scanning NV kind of platforms. There's another company I think from Christian Degen, also one of the pioneers of the technique of scanning NVs, also in Switzerland.
can you just plug it into like AFM, or it needs to like
it's basically an AFM platform that comes with all the optics, etc.
optics?
And
I
tips.
see like the lasers.
Yeah, everything. And you can, so in principle, if you want to do scanning magnetic field sensing with NVs, these are tools that you can buy today.
I see. I know. Is there like a list of unknown phenomena or things to be understood or decoded? Like what is not clear that you would like to bring your tips to bring more information to the world?
So I think there are always a list of things that I would love to have kind of sensors. Many things I don't even know what quantity to sense that would give me this kind of information. So interesting phases, correlated phases, have underlying entanglement in them. So what probes would be suitable to detect the underlying entanglement of that phase is interesting. So people talk, for example, about what's called entanglement entropy.
Mm-hmm.
It basically says, suppose I have a system. Suppose I have, a system, non-interacting system, okay, like a crystal. And if so entanglement entropy basically asks the following question. What happens to the system if I split it in half? Does the energy of the system goes up? Or if it's made out of two components that are anyway separable, it doesn't matter if I cut it in half. I mean, there is surface energy, etc., but let's ignore that. But did I do anything special to the underlying constituents by kind of splitting it in two and then connecting it back? And it turns out that things that have, you have surface law and volume law for how the entropy would grow, whether it grows with the surface size of the sample or its volume. So if, there are some interesting experiments that Marcus Greiner here is doing to try and measure this kind of entanglement entropy. So these are interesting type of probes to try and develop. There are interesting ideas known as the quantum Fisher information. These are quantities, again, that can tell you something about the degree of entanglement inside the system. So we're trying to push to develop ways of measuring this kind of Fisher information. Questions that we'd love to have a direct way of measuring is, as I said, suppose I have a superconductor. I want to know what's the underlying order parameter. Is it S wave? Is it P wave? Is it D wave? We're developing various microwave probes now that in principle might shed some light on that. But it would be great if we had them, and if they do exactly what we want. I don't know. Another question is, you have superconductors. Some of them can break time reversal symmetry. This is really interesting. Because superconductivity is a medium in which you can imagine hosting non-abelian particles like Majoranas.
Mm-hmm.
But if you wanted to be able to separate Majoranas to do quantum computing with them, you need to break time reversal symmetry. So you need superconductors that break time reversal symmetry.
Do we have one? Or
so probably yes. But you need them to be controlled, etc. And the hard part is that, when you do a Hall measurement, you measure conductivity. If you see a Hall effect, you know you've broken time reversal symmetry because the Hall effect changes sign when the direction of time changes. So anytime you have a Hall conductivity, you know, great. The problem with a superconductor is that it has zero resistance at low frequency. It's at DC. So even if you have a Hall conductivity, it gets shunted by the zero resistance of the superconductor. So both Hall and longitudinal conductivity of a superconductor vanish at zero frequency. So what you'd like to do is to be able to measure the Hall conductivity at finite frequency. That's why we're developing these kind of high-frequency probes, partly because we'd like to probe the Hall conductivity of materials and see if they break time reversal symmetry. People measure some very beautiful experiments at Stanford by Aaron Kapitolnik, for example. They use K-rotation, basically. So if you take light and you send it on some material, the polarization of the light would rotate if it breaks time reversal symmetry. And it's a way of measuring the Hall conductivity, but at a frequency that's given by the frequency of light. And typically that frequency is much, much above the gap. So what we're hoping to do is to develop probes where it can measure the Hall conductivity on frequencies that are below or comparable to the gap. That's why you need microwaves or hundreds of gigahertz or terahertz, depending on the but you need kind of that frequency range is really interesting. So there are many, many challenges ahead to figure out.
Yeah, I think it's this non-abelian particles like Majorana is really hot in,
Yes.
in both like in press science everywhere.
Yes,
If
yes.
you could,
But yeah.
So also, like from your perspective, where are we standing? And because there's like some works like Report OK, we have observed some of those Majorana zero modes. Then there are the papers. Oh no, there's no such modes at all. Or what's your take in general? Like what's happening in the field?
Yeah, I think there's a lot of controversy in the field because apparently, one of the hard things about science is that you can't prove anything. You can only disprove things. And so, if you have an experiment and that experiment is consistent with multiple models, even, suppose that experiment is consistent with a model. It doesn't prove the model, right? It says it's consistent with the model. And then what makes things hard is if you find another model that describes the same experiment. Because now you need to figure out, well, how do I distinguish between these two models? What's really going on? I think that's where the field is kind of at, is trying to understand whether, the physics that they're seeing is really Majoranas or it's coming from disorder. There is a big problem with the specific platform, I think, that they're using, and that is that it's very hard to improve the quality of the samples. If you try to make the gaps bigger, the superconducting gaps bigger, you increase the disorder as well. So even though, it's kind of very as clean as you could probably get it in these platforms, they're not easy to work with. And I think the problem,
How's the disorder?
So what happens is that you proximitize a semiconductor, right? And if you, so you need the superconductor to be very close to the electrons, but the interface between the superconductor and the semiconductor is disordered. It's very hard to control precisely. There are going to be some always dangling bonds, things that are happening there. So if you want the proximity effect to be stronger, you need to bring the superconductor closer. So now you're bringing all the disorder closer as well. If you move the superconductor further away, so the disorder is weaker, but now your proximity effect is also weaker. So your induced gaps are smaller. So
it's essentially a challenge of stitching two types of materials.
Yes, it's
and from materials perspectives, probably like the strains the materials would feel.
Oh, there's definitely strain, dangling bonds. These are problematic. Yeah. There's some new opportunities that are arising now in layered materials, for example, where now you can have one material which could have, which could be a superconductor. Just by gating, you increase the density, it becomes superconductor, and then nearby, it's a semiconductor. And so now everything becomes, there are no interfaces because everything is happening within one material that can simply demonstrate different phases that you need in order to create these kind of hybrid structures. So these are really interesting.
Are those like the multi-layer systems, or it's a different
yeah, so
class?
for example, if you imagine, one thing that we've done, we haven't talked about today, but was to realize that in order to generate a topological superconductor, one that would host Majoranas, you don't need any topological ingredients. This was realized already, very early on, but in our case, we were considering a Josephson junction. So superconductor and other superconductor separated by a 2D material. And the only thing that you needed in it was spin-orbit interaction. So it doesn't need to be topological or anything like that, but we could show that in this SNS with spin-orbit here, you could have Majoranas at the ends of this junction. So now you can imagine, but we did it with a real superconductor like aluminum and niobium, and the semiconductor was mercury telluride. But now you can take just twisted graphene. Maybe that's not the best example. Maybe tungsten telluride is a better one because twisted graphene doesn't have strong spin orbit. But maybe tungsten telluride, or at high density, it becomes superconductor. So you have just one layer. You have a gate here, you have a gate here, and you have a gate here. You tune the two sides to be superconductors and the middle to be a normal semiconductor. And now you suddenly have a platform that could potentially host superconductivity that could be topological with Majoranas, very little disorder in this entire system. So these are kind of new directions. Even more interesting, so Majoranas are only one type of non-abelian particles. There are things that are called parafermions, which have even more complex braiding statistics, what happens when you braid particles. And these can emerge when you hybridize, for example, a fractional quantum Hall state with a superconductor.
And this so far comes like from theory, right?
This is all theory. When you hybridize...
Hopefully we're not going like, in this area, like the string theory.
No,
where you have but at least you can show experimentally or get some proof out of it.
Yes, I mean, that's the idea. But the challenge is, so these theories initially came about when you had, you try to create a hybrid between a superconductor and fractional quantum Hall effect. But fractional quantum Hall effect traditionally appears at very large magnetic fields. The superconductor doesn't like that. So how do you marry these two? But now, in layered materials like twisted MOT2, you can get fractional phases at zero magnetic field.
Wow.
These are called fractional Chern insulators, and you could basically see that the system behaves like a fractional quantum Hall state, zero magnetic field. So now you can marry a superconductor with these fractional phases at zero magnetic field, giving you, again, interesting possibility to realize these parafermions. So I think the field is really broad. And I think that in these kind of new directions, there's more and more groups who are trying to and interested in doing it. I think there is less work on kind of the real original approach, which is 1D wires proximatized by superconductors, semiconductors proximatized. I think people are kind of looking to these new platforms that can create novel hybrids. So fundamental research kind of applications are far away yet, but could be really interesting. Yeah.
I see. Just curious. So you have, the tool or like the hammer to apply to so many nails, like maybe like in general, how do you choose like maybe the problem to work on, like the sample to apply your tools, or how to build your tools, if you could?
Right, it's an excellent question, and often I with prospective students who come and are interested in joining the group, they kind of ask, so how do you choose what problems you're working on, etc. And I tell them, kind of my guiding principle is always, you don't want your system to be too simple. because really what we're after are surprises. If you do an experiment, I tell my students, and the experiment succeeds, it's a failed experiment. Because we haven't learned anything new, right? You did an experiment, you spent a year or 2 years trying to see whether some theory predictions is right, and then you found that it's consistent with that paper, then okay, what did we, well, we learned that it's consistent, that's nice, but it's much better if you find something that's missing in that theory, and that pushes science forward, right? You need to modify the theory and then make some new predictions, etc.
It's like a ping pong between theory and experiment.
Precisely. And the way that moves forward is only by finding things that the theory did not predict. So the guiding principle for finding surprises is complexity. Because if you have a system that's too simple, the likelihood that you would be making a prediction about it that will be correct is very high because you understand it well. It's simple. So that's why many body physics, collective phenomena, emergent phenomena is a great playground because physics is complex. Now, you don't want things to be too complex, right? And when we're developing a technique, a new method, for example, we actually want to see what we expect because the first thing you want to do when you develop the new technique is to try it on something that you know should work. So there you want to have an agreement between your hypotheses and what you expect, but then you want to immediately apply it afterwards to something unknown, and hopefully that is complex enough that will give you something unexpected. For example, when we were starting to do these kind of spin wave experiments, scattering of spin wave experiments, we said, oh, let's apply it to something that's really simple. We'll put another magnet on top of our slab, and that was already too complex. We're still figuring out exactly what's happening in that system. So sometimes it's very hard. We're developing new techniques to measure properties of superconductors, etc. And these need to be layered superconductors for our techniques to work, 2D superconductivity. But there aren't that many that we understand well. So you're in a position where you're struggling to understand. You're developing a new technique and you're developing it on systems that you don't really understand very well. So that becomes a complicated challenge because you don't know you don't understand the physics of the material you're studying, or you don't understand your technique.
Right.
Where is it coming from?
Yeah, I think it's an irony of research that we probably discussed with other speakers, that indeed some of the problems simple from the very beginning, but turn out to be very complex. And the opposite is also could be, sometimes could be impossible, but
turns out
you tune it a little bit here and there and it is all. So right. Do you see that, especially like with recent developments in like machine learning models, like data science, AI, does it help to, increase the bar in terms of understanding of the data you collect?
I think these tools are going to become incredibly important, right? You can find correlations in data that you were not able to realize that existed before, things like that. So, we're definitely keeping an eye on these tools. Whether one could really implement. I mean, I think at the moment AI could help you in doing data analysis if you have a lot of complex data, etc. But it can't really very easily help you run the experiment, right? It would be really good, and I know that there are companies and efforts to develop these kind of things where, as you're setting up an experiment, you will have some AI companion that can help you in, suppose you're trying to tune your optics, right? If you had an AI companion that would say, no, turn that mirror, align that mirror, kind of, that would be really nice. But I think these are kind of still a little bit far away, maybe not too far away, but I think there will be more and more AI companions that help us do things in the lab.
Or do the alignment mirrors even without telling you. Just
exactly. They would just
do the fiber coupling. Done.
Exactly. Just go. Yeah, that would be nice.
Do you have advice for the younger generations of scientists like entering the fields? And
So one thing that I think is really important is to be very agile as a scientist. Especially experimentalists, we face a few challenges, right? Our experiments are expensive. Our instruments cost a lot of money. You need to, and sometimes what this means is that you tend to get stuck with a technique. And I think this is not good. I mean, this is kind of a local minimum that is really good to be in a state of mind that you try to escape. You want to be very agile and not be afraid to learn new techniques and kind of move on and try different things. Because if you're kind of become just a specialist in one particular thing, there could be a time in which that technique is very effective and useful for studying certain things, but then that time might pass, and then you're kind of in a position where you have a tool that's, not really able to provide insight into interesting questions, modern questions. So my advice is to not hesitate to try and kind of jump onto new techniques. Usually when you start something new, you're not going to be the expert, but over time you will. So I think just be agile. Kind of, if you find an interesting physics problem that interests you, don't hesitate. Kind of, it's okay. Try to figure out how to do it. And if you are fascinated by a new technique, try it. You don't need to make huge strides, but just not get stuck doing one thing all the time.
It's like a one-trick.
Yes, exactly. You don't. I think that's not so good.
Yeah.
I think if I look at really kind of successful groups, these are groups that have been able to try out different techniques and different ways of looking at things over time, and so that kind of consistently allows you to generate good science over time.
Thank you, Amir.
Pleasure. It was intense. So
it's very insightful.